Good morning, everyone, and welcome. I am Dr. S.K. Singh, and I am pleased to be here today. Today, we will be exploring the basics of HPLC and GC, along with troubleshooting tips. This presentation is designed to give you a clear understanding of these essential techniques. We will cover fundamental concepts, common issues, and practical solutions to help you improve your analytical skills. I look forward to sharing this knowledge with you. Let's get started. Chromatography is a critical analytical technique that we use for separating, identifying, and quantifying different components within a mixture. It's essential in many fields, especially in pharmaceutical quality control, because it helps ensure the purity and potency of products. In the lab, the two most common chromatographic tools you'll encounter are HPLC, which stands for High Performance Liquid Chromatography, and GC, or Gas Chromatography. These techniques are widely used because of their precision, speed, and reliability when analyzing complex samples. This presentation will focus on several key aspects. First, we'll look at the basic principles behind these methods, how they actually work. Then, we'll review the main components of the systems, because understanding what makes up these instruments is crucial for troubleshooting and optimization. Next, we'll discuss the critical parameters that influence the accuracy and reproducibility of results, so you can better control your analyses. We'll also explore common issues that can arise during chromatography and how to systematically troubleshoot them. By the end, you'll have a clearer picture of how to operate, troubleshoot, and maintain these powerful tools in your lab, helping to ensure high-quality pharmaceutical products. Let's take a closer look at HPLC basics. HPLC, or high-performance liquid chromatography, is a powerful technique used to separate, identify, and quantify components in a mixture. It's widely used in various fields like pharmaceuticals, environmental analysis, and food safety because of its precision and efficiency. The key idea behind HPLC is that it uses a liquid mobile phase to carry a sample mixture through a column packed with a stationary phase. As the mixture moves through the column, different components interact differently with the stationary phase, causing them to separate over time. Understanding these interactions is crucial because they determine how well we can separate and analyze complex mixtures. The process involves carefully controlling variables like flow rate, temperature, and the composition of the mobile phase to optimize separation. Overall, mastering these basics helps us appreciate how HPLC can provide accurate, reliable data, which is essential for quality control and research. This foundational knowledge sets the stage for exploring more advanced aspects of the technique as we progress. Separation occurs based on the differential interactions of analytes with both the stationary and mobile phases. Essentially, different compounds will interact differently with these phases, which allows us to separate them effectively. The movement of these analytes through the system is driven by a high-pressure mobile phase that is pushed through a tightly packed column. This pressure ensures the mobile phase flows steadily and efficiently, carrying the analytes along. As the analytes travel through the column, they don't all come out at the same time. Instead, each one elutes at a different time, which we call the retention time or RT. This difference in elution times is fundamental to how HPLC separates and identifies compounds. So, in summary, HPLC relies on these differential interactions and the controlled flow of the mobile phase to achieve precise separation of complex mixtures. Let's take a closer look at the main components of an HPLC system. First, we have the solvent reservoirs, which store the mobile phase solvents that are essential for the separation process. These reservoirs feed into the degassing system, which removes dissolved gases from the solvents to prevent bubbles that could interfere with the analysis. Next is the pump, which can be either isocratic or gradient. This pumps the mobile phase through the system at a consistent flow rate, ensuring stable conditions for separation. Following that, we have the injector, which can be manual or automated with an auto-sampler, responsible for introducing the sample into the system precisely and reproducibly. Then, the column itself. There are various options like C18, C8, phenyl, or HILIC, each selected based on the specific separation needs of your analytes. The column is where the actual separation occurs. After the column, the detector comes into play. Options include UV, PDA, RID, or FLD detectors, which identify and quantify the separated compounds based on their unique properties. Finally, all the data collected by the detector is sent to the data acquisition system, typically chromatography software, which processes and displays the results. Understanding these components and how they work together is fundamental to mastering HPLC analysis, as each part plays a crucial role in achieving accurate and reliable results. Now, let's take a closer look at some of the critical HPLC parameters that can really influence our results. First, the mobile phase pH, composition, and gradient program are fundamental. These factors control how well our analytes are separated and can affect the peak shape and resolution. Adjusting the pH, for example, can change the ionization state of analytes, impacting retention times. The composition and gradient program help us fine-tune the separation process to achieve optimal results. Next, the flow rate is another crucial parameter. It determines how quickly the mobile phase moves through the column, impacting both the analysis time and the resolution. Finding the right flow rate is a balance. Too fast, and we might get poor separation. Too slow, and our analysis becomes unnecessarily lengthy. Column temperature also plays a significant role. By controlling the temperature, we can influence the viscosity of the mobile phase and the interaction between analytes and the stationary phase, which can enhance reproducibility and peak shape. Injection volume is another key aspect. Injecting too much can cause peak broadening and overload the column, while too little might reduce sensitivity. It's about finding that sweet spot for accurate, reliable detection. Detector wavelength should be chosen carefully based on the analyte's absorption characteristics. Selecting the optimal wavelength ensures maximum sensitivity and specificity in your detection. Finally, the column chemistry and particle size are fundamental to the separation process. Different stationary phases interact differently with analytes, and smaller particle sizes typically provide higher resolution but may require higher pressure. All these parameters, when optimized, are critical to achieving reliable, reproducible HPLC results. They connect directly to our overall goal of precise analysis, ensuring we get accurate data to support our research or quality control processes. Let's talk about some common issues you might encounter with HPLC. One of them is no or low pressure, which can happen if the flow rate is too slow or there's a leak in the system. On the flip side, high back pressure usually indicates a clog or a blocked column, and that can really impact your analysis. Retention time shift is another problem. It means your peaks are not appearing where you expect them to, which can throw off your results. Poor peak shape, like tailing or fronting, can make quantification tricky and often points to issues with the column or sample preparation. You might also see split peaks or ghost peaks. These are extra, unwanted signals that can confuse your interpretation. Baseline noise or drift is a common nuisance, causing fluctuations that make it hard to distinguish real signals from background. Carryover, where traces of previous samples linger in the system, can contaminate your next runs and skew your data. All these issues are classic problems in HPLC, and understanding them helps us troubleshoot efficiently and keep our analyses accurate and reliable. Let's start with high back pressure. When you notice this, it's often caused by issues like blocked frits, contamination inside the column, or even excessive viscosity of the mobile phase. To troubleshoot, you can try replacing the frit, flushing the system in the reverse direction, or replacing the entire column if needed. Also, checking the mobile phase filtration can help prevent future blockages. Next, we have retention time shifts. These can happen due to pH variations, errors in mobile phase mixing, or deterioration of the column over time. To address this, prepare a fresh mobile phase, ensure that your gradient is functioning properly, and stabilize the temperature of your column. Consistency here is key to reliable retention times. Moving on to poor peak shape. This is often caused by overloading the column, void formation, or pH being outside the optimal range for your analyte. To fix this, reduce your injection volume, consider replacing the guard column, and make sure your pH is close to the analyte's pK for best results. Finally, let's talk about baseline issues. These can stem from detector lamp aging or problems with degassing the mobile phase. Replacing the lamp can often resolve this, as can improving the degassing process. Using high-purity solvents also helps maintain a stable baseline. Understanding these common issues and their solutions is essential for maintaining the performance of your HPLC system and ensuring accurate, reliable results. Let's move on to Section B, which focuses on GC basics. In this part, we'll explore some fundamental concepts that are crucial for understanding the broader topic. I'll explain these key points thoroughly, but in a conversational way, so they're easy to follow. As we go along, I'll highlight the most important ideas to keep in mind. These basics will serve as a foundation that connects to the overall theme of our presentation. So, let's dive into the essentials of GC and see how they fit into the bigger picture. Let's talk about how separation occurs in gas chromatography. The key idea here is that separation is based on two main factors: the analyte's volatility and how it interacts with the stationary phase. Essentially, compounds that are more volatile tend to move faster through the column, while those that interact more strongly with the stationary phase tend to stick around longer. Next, we have the role of the carrier gas, which can be helium, nitrogen, or hydrogen. This gas acts like a conveyor belt, transporting the vaporized sample into the column. The choice of carrier gas can influence the efficiency and speed of separation, so it's an important consideration. Now, once the sample is inside the high-temperature column, separation occurs based on boiling points and polarity. Compounds with lower boiling points vaporize more easily and move faster, whereas those with higher boiling points tend to lag behind. Similarly, polarity affects how compounds interact with the stationary phase, further aiding in their separation. All these principles come together to give us a powerful technique, gas chromatography, that allows us to analyze complex mixtures effectively. It's all about leveraging these physical and chemical properties to separate and identify the analytes with precision. Let's take a closer look at the core components of a GC system. First, we have the carrier gas supply, which is essential for transporting the sample through the system. It's usually an inert gas like helium or nitrogen that ensures smooth flow. Next, regulators and flow controllers are critical. They help us maintain precise control over the gas flow, which directly impacts the separation quality. Moving on, the auto-sampler or syringe injector automates the sample introduction process, making analyses more consistent and efficient. The injection port, which can be split or splitless, is where the sample actually enters the system. Choosing between split and splitless modes depends on the sample concentration and sensitivity requirements. The column is at the heart of separation. It can be capillary or packed, and different phases are used depending on the analytes we're targeting. The oven surrounding the column can be temperature programmed, allowing us to optimize separation by controlling the temperature profile during analysis. Detectors are vital for identifying and quantifying the compounds. Common types include FID, TCD, ECD, and MS, each suited for different detection needs. Finally, the data system collects, processes, and displays the results, tying everything together into a coherent analysis. All these components work in concert to deliver precise, reliable chromatographic separation and analysis, which is the overarching goal of the GC system. Let's take a closer look at some of the critical GC parameters that influence our analysis. First, the injector temperature is vital because it needs to be high enough to vaporize the sample quickly without causing decomposition. Next, the oven temperature program plays a key role in separating compounds effectively. Adjusting the temperature over time allows for better resolution. The split ratio determines how much of the injected sample actually enters the column, which is essential for controlling sensitivity and peak shape. Carrier gas flow is another crucial factor. It affects how quickly the analytes travel through the column, impacting separation quality. When considering column dimensions and film thickness, these physical characteristics directly influence the efficiency and selectivity of the separation process. Then, the detector temperature must be optimized to ensure consistent and reliable detection of our analytes without introducing noise. All these parameters, collectively called the critical GC parameters, are interconnected. Fine-tuning them helps us achieve accurate, reproducible results and ultimately supports our goal of robust analysis. Remember, understanding and controlling these settings is fundamental to mastering gas chromatography. Let's talk about some common GC problems that can affect your results. First, no peaks or broad, tailing peaks can indicate issues with the injection process or column performance. Broad peaks, for example, often suggest column overload or poor efficiency. Tailing peaks can be caused by active sites on the column or sample interaction issues. Overlapping peaks are another challenge. They make it difficult to distinguish compounds, especially in complex mixtures. Ghost peaks, which are unexpected signals, can sometimes be due to contamination or carryover from previous runs. Baseline drift is another common issue, where the baseline doesn't stay stable, often caused by temperature fluctuations or detector problems. Poor reproducibility can be frustrating and typically points to inconsistencies in sample preparation, injection, or instrument conditions. Leaks in the system can lead to loss of sample or carrier gas, resulting in poor sensitivity and unreliable data. Speaking of sensitivity, poor sensitivity can mean you're missing low-level compounds, which might be due to detector issues or sample preparation. Overall, these problems can significantly impact the accuracy and reliability of your analysis, so being aware of them helps in troubleshooting and maintaining your GC system effectively. Let's start by looking at the first common issue, no peaks or low response. This can often be caused by injector blockage, leaks, or incorrect injection techniques. To troubleshoot this, I recommend cleaning the liner, checking the septum for any damage, and verifying that your auto-sampler settings are correct. These steps help ensure the sample is properly injected and detected. Next, we have tailing peaks. These usually happen when the inlet liner is dirty or when there are active sites in the column. The solutions here include replacing the liner, trimming the column if necessary, and deactivating the injection port to prevent interactions that cause tailing. Recognizing tailing peaks helps us identify potential column or inlet issues early. Moving on to peak broadening, which can be caused by low injection temperatures or dead volume in the system. To address this, increase the inlet temperature to improve vaporization and replace inlet seals if they're contributing to dead volume. These adjustments help sharpen the peaks and improve resolution. Now, let's discuss baseline noise and drift. These are often due to contamination in the carrier gas or poor conditioning of the column. Using high-purity carrier gas and properly conditioning your column can significantly reduce noise. Additionally, checking for leaks in the system ensures stable baseline performance. Finally, ghost peaks are caused by carryover or contamination within the injector. To resolve these, perform bake-out procedures to clean the system and replace the septum or liner if they are contaminated. Eliminating ghost peaks is essential for accurate, reproducible results. By understanding these common issues and their solutions, we can maintain optimal chromatographic performance and trust the data we generate. Let's move on to Section C, which covers best practices. In this part, I want to emphasize the importance of thoroughly explaining key points, but I also encourage a conversational tone to keep the audience engaged. Highlighting the most important concepts helps ensure they resonate and are remembered. Connecting these points to our overall presentation theme is crucial, as it creates a cohesive narrative and reinforces our message. Remember, the goal is to communicate clearly and effectively, making sure our audience understands and stays interested throughout. Let's start by emphasizing the importance of regular filter replacement. Changing filters routinely helps maintain optimal system performance and prevents contamination. Next, it's crucial to check the pump seals and pistons regularly. Ensuring these components are in good condition helps avoid leaks and maintains pressure stability, which is vital for accurate results. Moving on, proper column flushing and storage protocols are essential. Flushing the column after use prevents buildup of residues, and correct storage ensures the column's longevity and consistent performance over time. Additionally, routine calibration and system suitability tests are key aspects of preventative maintenance. These checks verify that the system is functioning correctly and producing reliable data, reducing the risk of errors. Overall, implementing these preventative maintenance practices in HPLC ensures the system's reliability, accuracy, and longevity, which aligns perfectly with our goal of maintaining high-quality analytical results. Let's talk about some key maintenance practices to ensure our GC system operates smoothly. First, it's important to replace the septum and liners periodically. This helps prevent contamination and maintains consistent performance. Next, regular leak testing is crucial. By checking for leaks frequently, we can catch issues early and avoid instrument downtime. Before using the column, always condition it properly. This step ensures the column is clean and ready for accurate analysis. Maintaining gas purity and flow stability is another vital point. Clean, pure gases and consistent flow rates are essential for reliable results. Finally, don't forget about preventive maintenance. Regular checks and upkeep of the GC system help extend its lifespan and prevent unexpected failures. Keeping these practices in mind aligns with our goal of achieving high-quality, reliable analytical results. When it comes to reliable chromatography, there are several best practices I always emphasize. First, always use HPLC or GC-grade solvents and gases. These high-quality materials help ensure consistent results and minimize contamination. Next, it's crucial to filter and degas the mobile phases. This step removes particulates and dissolved gases that could interfere with the analysis or cause fluctuations in your baseline. Stabilizing the temperature is another key factor. Maintaining a consistent temperature helps improve reproducibility and peak resolution. Using guard columns is also highly recommended. They act as a protective barrier for your main analytical column, extending its lifespan and maintaining performance. Following proper shutdown and startup procedures is essential too. This ensures your equipment remains in good condition and reduces the risk of introducing variability or damage. Lastly, always document all changes and observations during your runs. Keeping detailed records helps troubleshoot issues, verify results, and maintain overall quality control. By following these tips, you really set yourself up for successful, reliable chromatography that delivers accurate and reproducible results every time. Let's wrap up with some final thoughts on HPLC and GC performance. As we've discussed, their effectiveness really depends on controlling key parameters, maintaining good practices, and understanding the methods thoroughly. When we troubleshoot effectively, we can ensure the results are accurate and precise, which is crucial for meeting regulatory standards. Having a systematic approach to troubleshooting helps us prevent recurring issues, saving time and resources, and ultimately boosting our lab productivity. Remember, consistent maintenance and a clear understanding of your methods are the foundation for reliable analysis. So, in summary, focusing on these areas not only improves the quality of your results, but also helps sustain smooth, compliant operations in our labs. For further support, please contact us. We're here to help you with any questions or additional assistance you might need after this presentation. Don't hesitate to reach out. We want to ensure you feel confident moving forward. Thank you so much for your time and attention today. Your engagement is truly appreciated, and I look forward to seeing how you apply what you've learned.